Oh, hi everyone. Thanks so much for showing up for your math learning. It's our second chance at this lesson. My mic wasn't working last time, so I'm sure this time will be better. How could it be? None of you are here. All right, anyhow, we're going to be taking a look at exponential equations and logarithmic equations in the context of logarithms. We can solve exponential equations like this by converting the base to be the same thing. Just let's get rid of that weird cursor that got screenshot there. There we go. And so this is a trick that we can use with logarithms as well. So let's just dive in. Okay, so if we don't have the option to change the base, we can use the logarithms to solve, like if there's no common base available. And so we're going to see this a lot, particularly our power rule is going to be a big part of solving these logarithmic situations where we have an unknown exponent and we can manipulate logs to solve them up. So our basic strategy, first we simplify to a single exponential term on both sides. We might have to be using our exponent laws to do that. Then you take the log of both sides. It doesn't matter what base. Base equals, who cares? So generally we'll use log base 10. That's like a base 10 log. And that's going to be fine. It's going to suit our purposes just fine. And then we apply the power rule of logs and rearrange to solve for the unknown variable. Okay, so here's some examples. 6 to the r is equal to 51. Well, you know, if we had 36 or we had 216 on that side, we could do it, because that would be 6 to the power 2, and that would be 6 to the power 3. So I suspect r is going to be greater than 2 but less than 3. But not exactly. If we want to know the exact value, then this is the thing that we would do. We take the log of both sides after your eraser works. Okay, and so it would look like this. Log 6 of r to the power r is equal to log 51. And then we apply power law. So then we get r log 6 equals log 51. And then here, log 6, I mean, that's just the number that you have to raise 10 to get the value 6. It's going to be a little less than 1. Anyway, we're just going to divide by that. Divide by log 6. And then that gives us our exact value for r. So that would be log 51 over log 6. Okay, now let's get out our calculator. You're going to want to practice with your calculator about how to punch these in and get your approximate values. So here on my calculator I punch 51 and then I push log. That's the number I need to raise 10 to get 51. And then I divide it by 6. No, not 6, log 6. So I punch 6 and then push log. Your calculator is probably backwards. That's probably more intuitive, so you're probably fine. And there we go. We knew r would be between 2 and 3, and turns out it's very close to 2. It's 2.1. So r equals 2.2. So it was 1.9 or something like that. That's how these do. Okay. Could I get you to just tuck that door? Oh, Leo, can you tuck that door closed? Sure. All right. So with these, here I'm just going to add 5 to both sides, just tidy this up as much as possible. And then we get 11 raised to the power something, and that something is here, n minus 8 is equal to 59. So we want to know what power we need to raise 11 to get 59. To find that out, let's log both sides. So we have log 11 to the n minus 8 equals log 59. We apply the power law, so we have n minus 8. That n looks suspiciously like an r, so let's fix that. Log 11 equals log 59. Now we're going to divide both sides by log 11, so we have n minus 8 equals log 59 over log 11. And then, guess what we're going to do? We're going to add 8 to both sides. So that'll be the last thing we do. So this all cancels. And then we get n. It's approximate. This is the exact value of n, and that's my favorite way to give the answer. But we can also give the answer as some kind of decimal abomination. And that would look like this. You have 59, you take its log, you might type log 59, you divide by log 11 equals this, and then you add 8. 9.7, very 9.7. And there's our approximation. All right. Carrying on then, 5 times 6 to the 3m is equal to 20. Well, why not just divide both sides by 5? Simplify that a little bit. 6 to the 3m equals 4. Okay, we have to raise 6 to some power to get 4. I can predict that that power is going to be a little less than 1. So m must be a little less than 1/3. Okay, there is some simplification we can do here, but why bother? Just take the log of both sides. Log 6, and then the 3m, we apply power law there, is going to be equal to log 4. So that is to say 3m is equal to log 4 divided by log 6, but we can do one better. We can divide both sides by 3 as well. Okay, just multiply by 3 in the denominator on both sides. So that m is equal to this. That is our exact value of m. And you would punch it thusly. Take the log of 4, divide it by 3, and that's that. Divide it again by the log of 6. And we predicted this would be a little less than 1/3. Lo and behold, it's 0.26. That is a little less than 1/3. There's our approximate value. Okay, so this is how you would solve these just sort of calculation problems to find exact values for unknown exponents, or their decimal approximations to whatever degree you wanted of accuracy. All right, okay, now, of course, we can apply these in application situations, in engineering, in finance, in science, not just mathematics. So we can do that with these types of formulas where P is our initial value or our principal investment. R is the growth factor. Okay, so let's say something was gaining 20% every month. What's this thing? Let's say Miley Cyrus mentions. All right, and we want to have a formula for this. Right now it's like 100,000 per day, and it's growing by 20% per day, let's say. All right, so our function, okay, here P would be the amount of mentions would be equal to 100,000 multiplied by 1 plus 20%. 20% is 0.2, and we would raise it to the power t, where t is days. A simpler way to write that would be 100,000 multiplied by 1.2 to the t. Okay. Now I can put in t for some number of days, and then it'll show how many mentions she gets. Okay, let's keep going. So we have this new car. It costs $23,000. The value decreases by 15% each year. So the amount that it's worth is equal to the P multiplied by the 1 plus or minus the growth rate raised to the power time. All right. So here, A is equal to $23,000 multiplied by 1 minus 0.15 equals 0.85 raised to the t. Okay. Now we want to know how much it will be worth in 5 years. So the A is going to be the amount it's going to be is 23,000 times 0.85 to the 5, and then you just punch it. And you punch it. You can punch it in a number of ways. I would probably do it in Bedmas order, because it doesn't matter what order I multiply these things. So I go in and I just calculate the exponent first. I don't know why I used to the 3 there, just to the 5. So that's that, multiplied by 23,000. So it will be worth $10,205 in 5 years. And then you write out your full sentence, blah, blah, blah. You all know I can write a sentence, so I'm not going to prove it to you now. The sentence would sound like this. In 5 years, the car will cost $10,205. Okay, let's keep going. So we know this. We want to know, when will it only be worth $1,500? Like, someone's got their eye on it. They're like, oh, I can't wait to buy that car. But I only have $1,500 with which to do that. So how long do I have to wait? This is the question that they need an exact value answer to. So we have our function. So a is equal to, we know what it's equal to, 1,500, but we also know another thing that it's equal to, which is 23,000 raised to the multiplied by 0.85. That's our growth factor, raised to the power t time. And then we take the log of both sides. So log, oh wait, no we don't. Oh my goodness, jumping the gun. Then we do a division. So we have divide both sides by 23,000. Tidy up the bedmas as much as possible first. I mean, you can do it with log rules, but you don't want to do that. Why would you want to do that, you maniac? Okay, so then you end up with 15 on 230, which equals 3 on, take out the 546. Okay, so simplify your fraction if you want. You could just use that in a calculator, but I don't play that way. I do as much on paper as possible. I like to get it here. Then I take the log of both sides. So I have log of 3 on 46 is equal to log of 0.85 to the t. Apply the power law. Bring that down. Divide by log 0.85 on both sides. And then these have canceled, so that is the value of t. It's log 3 on 46 divided by log 0.85. So how would you punch that? First I'd do 3 divided by 46. That's my fraction. It's that nasty, untidy decimal. Okay, which you should never write down. Don't write that down. Okay, and then we're going to do the log of that. And then we're going to divide that by 0.85, the log of that. And that gives us 16.8. 16.8 equals time. And that's the very good approximate value, because I mean, we're talking like, when is this car going to be about worth $1,500? You need about 17 years. So then my sentence might be, in 16 years and about,
Can I go to the bathroom?
Yep, 10 months. Okay, that's how we would approach those. Okay, so this one is very similar, so I'm going to go very quickly. The only difference here really is that we're increasing. So we have this land that's worth $30,000 multiplied by the growth factor, which is 1.05. Please not 1.5. 1.5 would be an egregious error, raised to the power time. That's the amount that the land is going to be worth. That's using my formula. I'd usually copy it down, but you can tell I'm kind of rushing here. So now I need to know t is years after 1960. So we can do 2011 minus 1960. And that gives us 51. So it's 51 years in the future. All right, so now we say the amount is equal to $30,000 multiplied by 1.05 raised to the 51. That's for sure a calculator problem. How did people do this before calculators? I don't know. Something with slide rules, probably. But what would that even look like? I don't know. I want to learn. I now want to know. And then multiply that by 30,000. There, 361,223. Therefore, the land was worth $361,000 in 2011. Okay. When was the land worth double? Okay. This is like saying A equals 60,000 equals 30,000 multiplied by 1.05 raised to the power time, and then we divide, of course. So we're ending, really what we're looking for is when was the growth factor, the total growth, equal to 2. So we take the log of both sides. Log 2 equals log of 1.05. You'll forgive me for not writing the t up there. I apply power rule. And so then I get this expression that t is equal to log 2 over log 1.05. All right, let's evaluate. Clear. 2, but I take its log, divided by 1.05, but I take its log, equals 14.2. So after 14.2 years, okay, therefore after 14.2 years, this land doubles in value. That's what you needed to know. That's what we all wanted to know. All right, let's keep going. And then the last thing in this lesson is just many scales in science and in pop culture and in landscaping, okay, are logarithmic in nature. That is to say, if you increase by a certain amount, you're actually increasing by some multiplicative factor, not just like a linear factor. So like decibels, every time that it increases by 10, it's actually twice as loud as it was before, I believe. And the Richter scale also works logarithmically. pH, so we've got geography, we've got science. There's also science of a kind, or music, or lots of things. We got astrophysics, science. We've got, piloting a plane. And we've got here, this is the scale of like how crunchy or how chunky your landfill is, or your gravel. So we've got like from boulders all the way to gravel, to sand, to silt, to clay, to like colloids, to like tiny, tiny particles. And if you want a scale where you can fit like a boulder, or like boulders are like cobblestones, to small gravel, to tiny, tiny microscopic particles, and you want it all on the same scale, doing so linearly, where like if I increase from here to here, it moves it that much on the graph, how can I distinguish between small and very, very small? So a logarithmic scale allows you to graph that type of information much more effectively. If we ask you questions about these, we will give you the formula. That would be something I'd expect you to Google in the real world. So you don't need to memorize this stuff nor put it on a cheat sheet. It'll be provided. You just need to practice the practice problems. So do let me know if you have any questions. I am here to be your humble mass servant. And all the best, everyone. Bye for now.